sophomore as an outcome of mathematical research, and computational experiments as an inspiration and testing ground for mathematical ideas. But we're also interested in how algorithms and mathematical techniques can have an impact on scientific discovery. And so I think tonight's topic is definitely in that category. So this fall, ICERM has been proud to host a virtual semester program on computational and algorithmic aspects of gravitational wave detection and analysis. We seek to involve mathematical scientists in one of the most exciting frontiers of modern science and hopefully contribute to future advances. And we've been gratified to see a large number of researchers around the world participating in our workshops, our programming, and in this event, which is a great way to end the semester. I want to thank all the people that have contributed to the work of the semester program. I'm very grateful for Deputy Director Sigal Gottlieb for her tireless work championing this program. The organizers of the program also did phenomenal work, keeping the excitement and momentum of this initiative despite the global pandemic. I should say they did not sign up to run a program during a global pandemic. And so I'm really grateful that they did it despite all the adversity. I'm specifically grateful for Scott Field and Gaurav Khanna, who were the leaders of the organizational efforts. It's not a coincidence that Gottlieb, Field, and Khanna are all faculty at UMass Dartmouth. We're really grateful to the leadership of UMass Dartmouth for letting some of their best faculty help us build a community of researchers in this important subject. We couldn't do this work without the support of institutions like UMass, so thank you very much. So I would also like to introduce our first presenter today, so Richard Price. So he graduated from Stuyvesant and went on to earn a dual degree in physics and engineering from Cornell, and then a PhD in Caltech under the supervision of Kip Thorne. He's been a professor at Utah for many years and has taken subsequent positions at the University of Texas at Brownsville and MIT. He's also an adjunct faculty member at UMass Dartmouth. He is the editor of the American Journal of Physics, and he's done important work in the area that we're discussing today. So he's known for a result called Price's theorem. As a mathematician, it's very gratifying that a physicist can be known for a theorem. That always makes me happy. And so it explains how inhomogeneities and space-time geometry outside a black hole can be radiated away. And he's also contributed to pioneering numerical simulations on the emissions of gravitational radiation during the merger of two compact objects like black holes, which has turned out to be really, really useful in subsequent work for LIGO. And so I'm really grateful that he'll be able to be moderating and leading the discussion today. He's a fellow of the American Physical Society and the American Association for the Advancement of Science, and an author of some well-known books on general relativity. So I've spoken far too long already. So Richard, please, the floor is yours.
Thank you. My job as moderator is to introduce the next person, which is my friend for many years, Saul Teukolsky, who is also a student at Caltech and also did his studies with Kip Thorne. Saul is the Hans Bethe Professor of Physics at Cornell University. He became that in 1999, and he's a national member, a member of the National Academy of Sciences. And rather than just read about him, let me tell you really about what Saul has done. Way back in the 70s, we were trying to get some handle on how to understand black hole astrophysics. And Saul came up with the crucial equation that allowed us to take the impossible problem of calculating black hole mergers and turn it into just a very, very difficult problem. And that was the Teukolsky equation, funnily enough. But rather than work on the Teukolsky equation, he let other people do what was only the very difficult. And he went on to do the impossible. He was one of the leaders of numerical relativity, in which the full power of supercomputers was finally brought to bear on the real problem of the merger of black holes. Saul is going to start us out by giving a view of the field And we will follow that with a question and answer session with Kip Thorne, the mentor of us all. So.
Okay. Okay, let me just get my screen shared. Okay, can you all see that? It's okay, good. So to explain to you what my role is, it's helpful to think about stand-up comedy. So when you have a famous comedian who's going to do an act, that comedian will usually have what's called an opener. And the famous comedian is the closer. The job of the opener is kind of to warm up the audience, tell a few jokes and get them going, put them in the mood for the closer. And the key role for the opener, the key rule for the opener is not to be funnier than the closer. So I'm going to try to keep my jokes to a minimum, and we'll see if Kip can rise to the occasion and tell a few jokes. Okay, so I'm going to talk about black holes, gravitational waves, and big computers. So let's start by the question of what is a black hole? Now, if I were giving this lecture, in person, then what I would do is I would take my keys out of my pocket, throw them up in the air, and point out that the faster I throw the keys up, the more velocity I give them to start, the higher they go before falling back. And if I could just throw the keys at 25,000 miles per hour, the keys would actually keep going. They would leave the gravitational pull of the Earth. And so 25,000 miles per hour is the escape velocity from the surface of the Earth. Now imagine I could take the whole Earth and squeeze it down until it was very tiny, about that far across, the size of a golf ball. All that mass in that very small volume. Now, if you could somehow stand on the surface of this Earth mass golf ball, gravity would be much stronger because, as we know, the strength of gravity depends upon the distance from the source of the gravity. And you're much closer now to the center of the Earth. So the gravity on you is much stronger. And in fact, at about that size, a mass of the Earth, the escape velocity would be the speed of light. Since nothing can go faster than the speed of light, no matter how much I tried to throw my keys up, they would never escape. In fact, nothing could escape. I would have turned the Earth into a black hole. So the answer to what is a black hole, it's a region of space and time from which nothing, not even light, can escape. Now, of course, I could never make a black hole simply by squeezing down all the Earth, the Earth into the size of something the size of a golf ball. I couldn't assemble enough energy to do that. But nature can make black holes out of stars. Because after all, what holds a star up against its self-gravity is the heat, the thermal energy that comes from the nuclear reactions in its core. So if you have a star, like the sun, for example, that's used up all the nuclear fuel in its core, had all possible nuclear reactions go to completion, there'd be no more source of pressure from the heat to hold the sun up, and it would collapse down. Now, the sun actually wouldn't go all the way to a black hole. It would end up as what astronomers call a white dwarf. But if you had a star that was bigger than the sun, we're not sure of where the dividing line is, but around about 8 or 10 times the mass of the sun, maybe more, some people think 20 times the mass of the sun, it would collapse all the way under its self-gravity and turn into a black hole. So that's how we think at least many of the black holes in the universe are formed. Now, a milestone that I'm going to talk about more in a minute is 2015. Right? Before 2015, astronomers would report every now and again they'd observed a black hole. And, the newspapers would say, black hole discovered in center of our galaxy or some other black hole. But in fact, that was not true. What the astronomers had observed was a lot of mass in a small volume. If general relativity was the correct theory of gravity, then these were black holes. They had a surface, the event horizon, which had this property that if you crossed it, you could never come out. The geometry of space and time around the black hole would be warped in the way that Einstein's theory says, and so on. But we were really like the astronomers in this Harris cartoon, right? It's black, it looks like a hole, I'd say it's a black hole. We couldn't be sure that these were in fact real bizarre black holes as predicted by Einstein's theory. And what happened in 2015 and published in 2016 was the discovery of gravitational waves coming from merging black holes. Right? So I'll talk more about that in a minute. And the importance is that black holes are the quintessential strong gravitational field objects. They're the ultimately strong objects that can test general relativity in this extreme condition. Okay, so what are gravitational waves? So you can think of gravitational waves as these propagating ripples, the same way that if you dropped a pebble into a pond, the ripples travel out. Well, in the same way, if you smash two black holes together, pretty violent event, far away, these ripples of space-time curvature propagate outward. They have two polarization states, or, for the experts and so on, we don't need to get into that. The main thing is that if I imagine, I'm sorry, this animation here is not working in this presentation, but imagine a circular ring of little particles and a gravitational wave coming by. The circular ring gets distorted to an elliptical shape where the ellipse oscillates. And so you get a change in the distance from the center, a delta L, a change in the length. And the strength of the gravitational wave, which I've denoted by this quantity h, is just the fractional change, the delta L over L. So the stronger the wave, the bigger the fractional change that you get. Okay. So LIGO, which stands for Laser Interferometer Gravitational Wave Observatory, is one of the most incredible accomplishments of experimental physics. It's the physicist's analog, I would say, of the Great Pyramids of Egypt. So this was an idea that sort of had its birth in the 70s. And Kip, who we're going to hear from in a little while, was one of the key players in conceiving of LIGO and pressing to have it built and really recruiting people and just making it happen. It's a collaboration today of about over 1,000 scientists from 100 different institutions from 18 different countries. And this is the site in Hanford in the state of Washington. You'll see these two arms in an L shape going out. They're about 2.5 miles long. And inside them, in a steel tube a few yards wide, a laser beam shoots down in a very good vacuum to the end of the tube where there's a mirror that bounces it back. And if a gravitational wave comes down, the length of these arms changes. It's a delta L. And there's an interference pattern at this corner station. And by monitoring that pattern, you can detect very tiny changes, the delta L produced by the gravitational wave. Now, if they announced, the effect that we're looking for is extremely small. It's about 1/1000th the diameter of a proton. I mean, even physicists, when they first hear this, think this is crazy, because it is crazy. And in fact, if they were to report that they had detected this, nobody would believe them. They would think, oh, somebody slammed a car door in the parking lot. So they built another one. This is in Livingston, Louisiana. You can see the vegetation looks a little more luxuriant, but otherwise it's pretty much the same technology. There was an upgrade to the detector that was completed in 2015, and the first science run started in September 2015. We're just finished now what's called O3, the third observational run, completed earlier this year. There are going to be a couple more observational runs before we get to the full design sensitivity. And each run has had increased sensitivity. So by now, so the first event was actually detected in September 2015. I'll talk a little bit more about that in a second. By now, there have been roughly 50 events detected, and some of them, besides the whole bizarre idea of detecting merging black holes out at cosmological distances by this technique, which is on the face of it crazy, all kinds of surprising things. For example, there's one event where the mass of one of the components in the merger looks like it's too heavy to be a neutron star, but too light to be a black hole. So, what's going on? There are other events that have a mass where, according to theoretical astrophysicists, you shouldn't be able to make a black hole of this particular mass. What's going on? Is it something wrong with astrophysical theory? Are these black holes being made by a different mechanism? Maybe smaller black holes merged together to make this big object? Who knows? So lots and lots of surprises. All right, the third ingredient of what I want to talk about is a computer simulation. Traditionally, physics is divided into two categories, theory and experiment. Computer simulation is something in between that. Instead of a real experiment, we simulate the result of an experiment by using a computer to solve the theory for the case we're interested in. Now, there are lots of examples of this. For example, an airplane wing, traditionally, the way that you designed a new airplane was you would make a model of the wing and put it in a wind tunnel, and then put sensors on the model of the wing and measure things like, the lift and the drag and all kinds of interesting quantities, and then fiddle things until you designed your new airplane wing. To do this with a computer, what you do is you select a grid of points on and in the neighborhood of the wing, and you use the equations of fluid dynamics to describe how airflow changes in response to the forces because you've stuck this wing to interrupt the flow of the air over it. So the computer keeps track of the air at each point, the density, the speed, the direction, temperature, and so on. And in fact, if you've ever flown in a Boeing 787 Dreamliner, this was the first airplane that was completely designed by computer simulation. There were no wind tunnel tests at all. So the first time a test pilot got in the plane and flew it was the first experimental confirmation that the computer simulation worked. And well, that's where we are. So now turning to binary black holes, here is a sketch that Kip has made. it shows the black holes with this sort of swirling motion because they're supposed to be spinning about their axis, dragging space and time around in their neighborhood. So there's an early phase when they're well separated. And underneath, you'll see a sketch of H, the waveform, the signal we would expect LIGO to measure. And it's labeled known because when the black holes are far apart, gravity is relatively weak, and we can use analytic techniques, pencil and paper techniques, to predict what the waveform should look like. Then when the black holes get close together and actually merge, that's when gravity is at its strongest, and that's where we need the computer to actually carry out the simulations. And then after the black holes have merged, we have a single black hole that kind of oscillates and settles down, finally ending up as just a stationary black hole. And that's labeled known. That's again where you can use analytic techniques, and that was the stuff that was related to what I did in my thesis. Okay. So here's a result of a computer simulation. This shows a big black hole and a small black hole going around it. The colors are coded to represent the fact that the black holes are spinning. So there's a spin axis that you can sort of infer from the gradient of those colors. Now, if this was Newtonian gravity, the orbit would stay in a plane. There would be nothing to break the symmetry between up and down. But because the black holes have a spin, the effect of gravity is different. There's a kind of a magnetic analog of the gravitational force, and that tilts the orbital plane, and you can see how that's happened. And then finally the black holes merge, and now you get this sort of ringing down, and you end up with the final black hole. And just to emphasize, you know, this is not an artist's conception or anything like that. This is, you know, many, many thousands of hours of supercomputer time to first do the calculation to get the gravitational waves that are emitted by this event. And then also even just to do the simulation, this visualization, to trace out the actual surface of the black hole, we had to probe the geometry with light rays and see which light rays got out and which were trapped to get the surface of the black hole. So this is actually, you know, no modeling or anything like that. It's a real solution of Einstein's equations. All right, so here is February 2016, the headline of the New York Times. You'll see the headline, "Cosmic Chirp from Black Holes Colliding Vindicates Einstein." And this was the first announcement of black holes merging black holes from LIGO. And this caused a big sensation. You know, you can see German newspapers, The Economist in London, all over the world. This was a big event. So here is the discovery paper. This is a figure from the discovery paper. So first of all, in the top left, you'll see the raw signal. It's been cleaned up just slightly from Hanford. And on the right, the signal from the other detector in Livingston. And what they've done is taken the signal from Hanford and superposed it on the one in Livingston. And you don't have to do any fancy statistics to just see by eye. You're seeing the same event. They even have to allow, there's a little light travel time because the distance to Hanford and the distance to Livingston from the event differ by a few milliseconds, and they have to put that little offset in. And then underneath, they've taken these signals, cleaned them up a little bit, removed some of the noise. And if you look carefully, there's a little gray broadening. That's to represent the uncertainty from the noise in the measurement. And then on top of that, you'll see it's labeled SXS waveform. SXS stands for our particular collaboration, simulating extreme spacetimes, it's called. And this is our prediction of what the signal should look like. And so one way to think about this is the LIGO detection tells you without any theory that they've detected gravitational waves from some extraterrestrial source. By comparing with the prediction from theory of these merging black holes, that's how we know that these were two black holes of roughly 30 solar masses each. And this, you know, when I first saw this was clearly, this was the high point of my professional career. I'd never believed that we would actually, first of all, that anything I was ever part of would ever have any, you know, experimental confirmation, and then that nature would be so bountiful to us to actually give us an event. Even if it was possible, why should, you know, this have been measured? It's unbelievable. And this is a statue of Einstein outside the National Academy in Washington, and you can see somebody put the sign there, "I told you so." And 2017, Nobel Prize in Physics to 3 of the people, including Kip, who were most responsible for producing this wonderful experiment. So I'm going to stop there and turn it over to Kip. Thank you.
Thank you, Saul. I hope everyone appreciates that Saul has given you an overview of 50 years of theory and 50 years of experiment and 50 years of computation. And he has been the opener. We now come to the closer, which is Kip. We have limited time, so I cannot begin to list all of his awards and all of his honors. I will just say again that he has won the Nobel Prize, which kind of indicates the level of scientist that he is. But it doesn't tell you about how he has been to the people in the field. He now lives in a house above the Rose Bowl in Pasadena because his group meets in the Rose Bowl. That is the size of his students and postdocs, or it was until he retired. He has been an inspiration to so many people in the field, and he has produced so many people in the field. He has created, he has populated the field. But I'm going on, and here he is, the closer. So before we start with the questions, I want to tell you the rules of engagement. I'm called the moderator, but I intend to be the modifier. I'm going to take the questions that were handed in, and some of them will, in almost all cases, those handing in questions were too becomingly modest to read the questions themselves. They want me to read the questions. In some cases, they want to have their names mentioned. In most cases, they want to remain anonymous. I am going to choose the questions so that I alternate between the more technical questions and the questions that have to do with, well, people, the sociology of science, questions whose answers might be of greater interest to a broader audience. I will also modify the questions when I think it's appropriate so that an audience, those without a PhD in physics, might better appreciate what the question intends. So let's start with a question from someone who chooses to be anonymous. The question is, gravitational wave has become an important part of science. How did you foresee that this would be the case when you started working in the field? Why, when you began, Kip, of all the areas you could choose to focus your intelligence on, why did you choose gravitational waves?
I think it was that I am not really a very good physicist, but I do have good taste. And And so that's the great thing about me. I have great taste, and I could see that if it was possible to detect these gravitational waves, they could revolutionize our understanding of the universe. And so I had to be convinced that it would be possible, and it took a few years to convince me because it seemed so outrageous that it could be done by this technique. I basically said of Ray Weiss that he was crazy when he proposed this technique that was used. But once he and others had convinced me that it could be pulled off, then I did decide that I would put as much energy from myself and my research group into trying to help them pull it off as I could, because the payoff would be so huge. But before we go on, I do want to make two remarks about other things that were said before I came on, if I may. First is about jokes. Now, Richard and Saul know I come from Logan, Utah. I come from a culture that cannot compete with them in jokes. And so they're talking about me being the stand-up comedian who brings down the house at the end. Was their form of joke on me? So shame on you for doing that to me now, Richard and Saul. Second remark is on October 3rd of 2017, in the middle of the night, I had a call from the Nobel people. The voice on the other end said, "It will not surprise you that you're being awarded the Nobel Prize together with Barry Barish and Ray Weiss for your contribution to LIGO." I said, "I'm not surprised at all, but I'm very disappointed." And I really was disappointed because the prize should have gone to the entire team that pulled it off. And the Nobel Foundation has an obligation to educate the world about the importance of big collaboration. That certain kinds of science can only be done in a collaborative, cooperative mode. And by focusing on the three of us, they were failing in what I think is their duty to educate the world about this. So I really do regard this prize as belonging to those more than 1,000 people who really pulled it off and made it possible. Okay, so now having said my piece, Richard, you can go ahead.
Okay, thank you. This next question might be related to that in some important ways, especially as it involves ICERM. The typical pattern in science is to use experiments to find or confirm a theory or discover some object, something like that. Something big, something small, an astrophysical object, a subatomic particle. The experimentalists have tools. They have many tools in their toolboxes. And it seems that in the detection of gravitational waves, there's a different pattern. There were two different searches going on at the same time, one involving a horde of brilliant scientists building incredible hardware, and another quest involving different brilliant scientists building incredible computer codes. And it's only a slight overstatement that both incredible quests had to be successful for the detection of gravitational waves. Has there been another example of something like this in which the two quests were going on simultaneously and needed both to be successful? And is the work of ICERM not only going to be a crucial tool, as computation has usually been, but is it going to be the main thrust or the equivalent or a co-equal part of the thrust for discoveries in the future?
Well, I could go on and on about this question. Let me try to be a little brief. Let me first give a bit of background on that underlies the question. It was already clear to those of us working on trying to understand sources of gravitational waves. It was clear by about 1980 that the first thing we would see would likely be collisions of black holes. It was also clear that we could not understand the observed waves from the collision without having a solution of Einstein's equations for the collisions of the black holes and for the waveforms, the shapes that came from the collisions. And it was also clear that the only way that you could figure out the predictions of Einstein was through computer simulations, solving Einstein's equations by numerical relativity on computers. And so that was 1980. So that was, I'm not very good at math. So 1980, 90, 2000, 2010, that was 35 years before the waves were discovered. And that was basically simultaneous with when Ray Weiss, and Ronald Drever, and others were just beginning to figure out how to build great big gravity wave detectors and beginning to build collaborations to do this. And so the two efforts started more or less simultaneously, but it was clear to me that you had to have the simulations at the same time as we were beginning to lay a roadmap for building the experiment. So I urged Saul Teukolsky and others working in that area to push hard. We needed the simulations by the time that the waves were discovered. And it's a long story, a 35-year story, but simulations did come in, but they were mature enough to really give us the answers only 2 or 3, 4 years before the first waves were seen. So it was pretty nip and tuck along the way. Are there other examples? Well, this is a particular example in the sense that not only was the simulations telling us what the wave shapes would be so we could figure out what we were seeing when the data came in, they also told us what's happening when black holes collide. And we didn't really understand that at all because we didn't have solutions of Einstein's equations. So we were understanding from the simulations what it was that was going to generate the gravitational waves. If I just say 2 black holes colliding cause the gravitational waves, that leaves a physicist kind of cold. What you really want to do is say the black hole collisions created a variable storm in the shapes of space and time, and we want to understand the details of that storm, the splashing of the sea, the tornadoes of water whirling around, actually tornadoes whirling in space around the black holes. And so all that had to be sorted out in simulations. So when the waves were seen, you would understand not only that the waveforms agreed with Einstein, but what was really happening to warp space and time when they collide. So that was really a massive effort of Saul and many others who were here in this workshop. There are a rather large number of people working in numerical relativity are participating in this workshop, and this workshop is been a major place for pushing forward now the frontiers and the techniques for the future in this area. Are there other examples? I'm not broad enough to know of other examples that are at this magnitude of how long it took and how completely essential the simulations were to not only to predicting what would be seen, not only to the data analysis, but also to understanding the fundamental phenomena that were going on. However, there are now, as the next phase, LIGO has seen colliding neutron stars, objects that are made from pure nuclear matter that collide and produce electromagnetic output of all sorts, gamma rays, X-rays, optical, infrared, radio waves. And in order to understand what is seen in those neutron star collisions, again, you need the simulations. The simulations are the key to interpreting what was really going on when those neutron stars were colliding. So that again is a central thing to what's happening at the present time here in this workshop. So it really is central. These simulations are central to the future of this field. And I know there are other areas of science where they are similarly central to making the science move forward hand in hand with experiment and observation. I think this is a particularly beautiful and extreme example in numerical relativity and LIGO's observations of gravitational waves.
Oh, thank you for a beautiful answer. And Kip, you made a joke about not being a good mathematician, but I want to give you a little coaching. When you came up with the 35 years, it would have been funnier if you had gotten the answer wrong.
Okay, I'll work at that. Thank you.
Okay, I think we're going to move now toward questions not about the physics, but about Kip. And the questioner will be Chris Johnson from the University of Utah, the founding director of the Utah Scientific Computing and Imaging Institute. Chris, go.
Yes, well, greetings from Utah, the former home of the Utah monolith. My question to you, Kip, is how did a kid growing up in Logan, Utah, become interested in physics and specifically in general relativity and find his way to Princeton and Caltech?
Well, when I was 13, about 1953, I went with my mother to Salt Lake City. I don't know what she was doing, but when we would go to Salt Lake, she would let me go out and wander the city. And so I found a used bookstore, and I found a little book, a paperback book used by a physicist named George Gamow. It had a title 1, 2, 3, Infinity. And it was all about mathematics and physics and cosmology. And I was totally entranced. I fell in love with the ideas of relativity, the ideas of higher dimensions, the ideas about the universe. And I never fell out of love. It was love at first sight. And so I then followed my nose. Where were the best places to learn about these things? And so here I am.
Great, thank you, Kip. The next question is from someone who will not remain anonymous. It is Ajit Gary, who asks, are there any prospects of multi-messenger astronomy for binary black holes? That is it feasible to foresee future light, visible light, and gravitational waves from the same binary black hole merger? And I think you can give us an answer some of us have already heard.
I don't know what answer you're expecting, but black holes themselves cannot emit electromagnetic waves. They cannot emit anything except gravitational waves. They can't emit neutrinos. You have to be made of matter in order to emit any kind of radiation other than gravitational waves. And black holes are not made of matter. They're made from warped space and time. So the only waves that they can produce are waves that are made from warped space and time, which is gravitational waves. However, when two black holes collide, they really shake up their neighborhood with enormously strong gravitational forces. So if in the neighborhood there is a lot of matter in the form of a disk of hot gas around one of the black holes or around the combined black holes, or in the form of a lot of gas or if you have the black holes collide and through this veritable storm in the structure of space and time with the collision, the black holes are given a huge kick and they go moving at very high speed through dense interstellar gas. Those kinds of things can produce electromagnetic emission. And so there is hope of seeing electromagnetic emission in multi-messenger astronomy through that. And there is actually some hint of that kind of thing having gone on in that a project called the Zwicky Transient Facility, which is a many institution project, which however is like LIGO, is headquartered at Caltech, but a different set of scientists. It has seen a signal that may be from that kind of a kick and a high-speed motion of a merged black hole through very dense gas, simultaneous basically with the gravitational wave signal. It's not clear whether they really are associated with each other. The gravitational wave data say this is rather farther away than the electromagnetic signal is coming from. But I think it's not out of the question because it is out on the tail of the distribution of how there is some finite probability that the actual gravitational wave source is closer than the best estimate is one way to say it. But it's a tantalizing example that may or may not be the real thing, but I do expect we will see the real thing, though the real thing will be rare.
Thank you, Kip. We have a question from April Khanna, who wants to know when your next movie will be out. When will there be a sequel to Interstellar?
So Christopher Nolan continues to tell me there will not be a sequel to Interstellar. I do have another movie that is maybe in the works, has been since, I guess we started it back around 2012 or so. So it's been in the works for a long time. These things go slowly. The basic story for this second movie was conceived in the form of a movie treatment by Stephen Hawking and Linda Obst and me. Linda was my partner on Interstellar, conceiving the original treatment that the movie came from. There is now a studio that has an option to make the movie from our treatment. There is a screenplay. They hired a screenwriter. There's a screenplay. There is no director yet. And in the midst of the pandemic, the whole issue of how you make movies is in flux. Everything is in chaos at the moment in Hollywood with the making of movies. And so we will see what happens after the pandemic. So now I've told you more than I've ever told anybody in public. I should keep my mouth shut. I don't know how much of it.
You're amongst friends. No one is going to blab, right? The next question will probably be something that doesn't have to be kept confidential. It comes from Ankan Sur, who asks, will gravitational waves be able to say anything about the Big Bang and how our universe started? You might want to include in that question when the universe started.
A long time ago, before I was born. See, I can tell a joke, my gosh.
You're getting better at it.
Not laughing hard enough. So anyway, so yes, in fact, this has been, for me, the most exciting dream about this field, the most exciting hope. We have known for quite some time that even if there has to be some minimum amount of gravitational waves are produced in the birth of the universe, and a minimum amount that is predicted by quantum theory. There had to be at least little tiny fluctuations of gravitational waves came off the Big Bang. And we've understood now for maybe 20 years, or maybe somewhat longer, that whatever came off the Big Bang will have been strongly amplified by what is called inflation in the earliest moments of the universe, when the universe was expanding very rapidly. So we have predictions for gravitational waves coming off the Big Bang, prediction of sort of a minimum strength for those gravitational waves if what came off the Big Bang was just these random fluctuations. And even with that minimum strength prediction, there is a good possibility for seeing them not by LIGO or any other LIGO-like instrument, but through their impact on what is called the cosmic microwave background radiation, or what is called polarization of this background radiation, which is a complicated story I don't want to go into. But there is a very good possibility that within the next 5 to 10 years, that will be seen definitively. There have already been hints of that being seen. And when that is seen, it will be really interesting to see whether or not the details of the inferred waves agree with what you expect if you get the minimum amount of stuff that came off of the Big Bang, or if they are very different because something different came off the Big Bang. And that, for me, that's the most exciting thing, is to be able to see what did come off the Big Bang. And I would expect, quite likely, that what we'll see is not from the minimum stuff that came off the Big Bang, because our understanding of the Big Bang is wrong. I look forward to our understanding of the Big Bang being proved wrong, and a real revolution in cosmology and understanding of the birth of the universe coming from those gravitational wave observations.
Thank you, Kip. I want to echo the thought that physics is most interesting when we turn out to be wrong. Another question from a questioner who wants to remain anonymous is, what could you comment on the possibility of detecting gravitational waves outside of the frequency range of LIGO and VIRGO?
Yeah, so LIGO and VIRGO and their future other partners all operate on gravitational waves that have frequencies of oscillation between about 10 hertz, 10 cycles per second, and a few thousand hertz. It's a pretty big band, a lot wider band than we have with our eyes looking at all the colors of the spectrum of the rainbow. Because if, say, from 10 to 1,000 is a factor of 100 in frequency. And the total actual range is more like 300 or 10 or 1,000 range of frequency. But nevertheless, that's tiny compared to all the possibilities. And so we know enough about the universe to be quite confident that there are very strong gravitational waves produced at much lower frequencies. Frequencies compared that of say 1/1000th of a hertz, or periods of a few minutes to a few hours. And to see gravitational waves, in this case, from stars falling into supermassive black holes or supermassive black holes colliding, or from neutron stars orbiting around each other, neutron star binaries that are seen as binary pulsars. To see gravitational waves from these kinds of things requires much bigger gravitational wave detectors. Bigger meaning detectors where the separation between the ends of the detectors, instead of being 4 kilometers, is more like the distance between the Earth and the Moon, or 10 or 100 times the distance between the Earth and the Moon. And so there are detectors of that have been conceived. The one that is most promising is called LISA. It was born really the brainchild largely of Peter Bender at the University of Colorado. And though others participate in the birth of the idea, but he has pushed it far more than others. It then became a joint US European mission. During the Bush administration, the US pulled out of it because of cost overruns on the new big space telescope. So it's now a European mission. But since LIGO's discovery of gravitational waves, and since a test of the technology for this by a test mission in space make it look very promising, the US is likely going to go in as a junior partner with the Europeans to make this happen. And this gravitational wave detector really is tremendously exciting in terms of the science that it's likely to do. And this is likely to reach fruition in the 2030s. There's one other possibility, and that's gravitational waves with even longer wavelengths or longer periods, lower frequencies from ultra supermassive black holes. And that is something that, in fact, I think will be seen by, again, yet a third kind of technology. Well, a fourth if we set aside the polarization of the cosmic microwave background. That is through timing of pulsars, that are things that send very precisely timed bursts to Earth from the distant universe that radio astronomers particularly study. And when a gravitational wave goes over the Earth, roughly speaking, clocks on the Earth slow down and speed up. And so that means that all the pulsars in the sky should simultaneously appear to have their pulse rates, the intertime between the pulses, slow down and speed up and slow down. And that technology is now quite mature, and we think it's called pulsar timing arrays. There's a big international collaboration for that. And that is, and the American part is nanograv. But this big collaboration, I think, is within a few years of success. So we actually have 4 different frequency bands in which we're likely to be seeing gravitational waves by the 2030s. This higher frequency band that LIGO and VIRGO operate in, the detector in space, the LISA detector at lower frequencies, the pulsar time arrays at still lower frequencies, and then this so-called cosmic microwave background polarization is still at lower frequencies. It's like creating optical astronomy, radio astronomy, X-ray astronomy, and gamma ray astronomy, all within about 20 years of each other. And it's really phenomenal. This is where we think this field is going.
And there's no telling what we'll learn. Let me just throw in a sad note that the primary instrument for the pulsar timing array was the Arecibo telescope, which committed suicide I think it was yesterday. So let me ask a question. The attempt to compute radiation from binary black holes has been in progress for a very long time. Numerical relativity started even before experimental relativity in detection of gravitational waves began. In 1994, the National Science Foundation issued a grand challenge to 40 researchers at 10 institutions to compute binary in spiral. But it wasn't until the middle of the first century of this millennium that real progress was made in doing those computations. Why was it so hard?
I think the issue is that all other forms of computer simulations, you're trying to simulate how things behave in space while time passes. You're trying to simulate how the flow of the atmosphere over the Dreamliner's wing occurs as time passes. That's something happening in space as time passes. With gravitation, with colliding black holes, you're trying to simulate something that itself is made from space and time. And so, how do you wrap your head around that? First, you're not simulating how something that happens in space as time passes. You're simulating how space and time themselves behave when they're highly warped. It's completely different conceptually. And what you have to do is turn that into something similar to other kinds of simulations. And doing that successfully was very, very hard. There were huge numbers of technical challenges. One that I like to cite particularly is that for a long time, the physicists who were doing this were not talking to the mathematicians. And so they did not fully understand the mathematical structure of the equations they were trying to solve. And it really was crucial to talk in greater detail with mathematicians and get a much deeper understanding of the structure of the Einstein equations in order to pull this whole thing off. And I think that was key to the ultimate success. And I think the SXS team that Saul leads particularly paid attention to that issue, but also involved bringing in people from the mathematics community to work hand in hand with people from the physics community to make this a big success.
Thank you. Our time is up, and it flew by amazingly quickly. I hope people in the who are watching and listening appreciated the clarity with which you gave those answers, Kip. I want to thank you for, on the part of everyone who took part in developing the ICERM program and setting up this webinar. Thank you, Kip. And so,
and a pleasure.
Brendan, do you want to close it out, or?
All I can do is to thank all of the moderators and presenters. So thank you, Kip and Saul and Richard. It's really fascinating to hear both the story of how this happened over 50 years and your perspectives on the future. And For those of you that have not been to ICERM public events before, we hold these every 4 to 6 weeks. And so keep tuned. We'd love to have you back at a future program like this.
Thank you, everyone. Bye-bye.
Kip and Saul, thank you so much.
Thank you. It's a pleasure. Richard's a great moderator.
And
Yes,
Segal,
you did a fantastic job.
Segal, thank you for setting this up and coordinating everything with the staff. And thanks to Bernadette and Brian and Matt for helping things go so smoothly.
My pleasure.
Yes, thank you.
It was a great talk.
Yeah.
It was wonderful. All right.
Bye-bye.
Good night.
Have a good night.
Thank you, Bernadette.
Thank you.